Welcome my dear learners for this course on finite element analysis. In our module 4, we were discussing about analysis of heat transfer problems. In our previous lecture, we have concluded our discussion on analysis of heat transfer through composite wall. From today's lecture, we will be heading our discussion towards analysis of heat transfer through extended surfaces, which are termed as fins. Fins are used in order to enhance the rate of heat loss through convection. As we all know, convection mode of heat transfer is governed by Newton's law of cooling. From Newton's law of cooling, the rate of heat loss through fins is given by convective heat transfer coefficient times the area, that is surface area for surface convection and cross-sectional area for end convection, times the temperature difference. The convective heat transfer coefficient cannot be increased or decreased. The only way to enhance the rate of heat loss through convection is by area. So if I increase the area, I can enhance the rate of heat loss. Therefore, the convection mode of heat transfer, which is given by HA delta T, considering the surface convection, the only mode to enhance the heat loss by convection through extended surfaces or fins is by increasing the surface area. If I increase the surface area, the rate of heat loss can be enhanced. So therefore, for any surface, let us say I have a surface maintained at around 200 degrees Celsius. Now, if I use fins of circular or rectangular cross section, I can enhance the rate of heat loss. So now, this 200 degrees Celsius of surface which is attached with extended surface, these are termed as fins. Cold air will blow over these surfaces and takes away heat. Thereby, one can enhance the rate of heat loss by using extended surfaces or fins, which in turn increases the area. Now, in our lecture 2 of module 4, we have derived expressions for element stiffness matrix and load vectors. In case of fins, the modes of heat transfer to be considered are conduction and surface convection for all the elements, whereas the end convection depends on the boundary condition given. So therefore, coming for the element stiffness matrix, one should know element stiffness matrix due to conduction, element stiffness matrix due to convection, that is surface convection, element stiffness matrix due to left end convection, element stiffness matrix due to right end convection. So coming for the stiffness matrix, one should know the formulas of stiffness matrix due to conduction mode of heat transfer is given by area of the element, thermal conductivity of element divided by length of the element, 1 minus 1 minus 1 1. Stiffness matrix of the element due to surface convection is given by H P LE by 6 2 1 1 2. H is convective heat transfer coefficient, P is perimeter, L is length. Coming for stiffness matrix due to left end convection will be given by H times the area 1 0 0 0. Coming for element stiffness matrix due to right end convection, we have H times the area 0 0 0 1. So these are the formulas one should know in element stiffness matrix. Coming for load vector, as we already discussed, all the 5 load vectors should be known to solve the problems on analysis of extended surfaces or fins for heat transfer. One is load vector due to internal heat generation, load vector due to flux, load vector due to surface convection, load vector due to right end convection and load vector due to left end convection. That is, coming for the load vectors, you should know load vector due to internal heat generation, that is, if heat generation is Q watt per meter cube, the formula is given by Q times area of the element into length of the element divided by 2 1 1. Unit is watts. The second load vector to be known is load vector due to heat flux, which is given by area of the element Q1 2. One important point to be noted in load vector due to heat flux is that heat added to the system is taken as positive, whereas heat moving out of the system is considered to be negative. Coming for load vector due to surface convection, it will be given by H P LE T infinity by 2 1 1, where H is convective heat transfer coefficient, P is perimeter, L is length and T infinity is ambient temperature. Coming for load vector, due to left end convection, we have the formula H times the cross sectional area into T infinity 1 0. Whereas load vector due to right end convection is given by H times the cross sectional area into T infinity 0 1. Before solving the problems on heat transfer through extended surfaces or fins, one should know these 4 formulas under element stiffness matrix and these 5 formulas to calculate the load vector. And for every element in the calculation of heat transfer for extended surfaces or fins, every element will have the stiffness matrix due to conduction and stiffness matrix due to surface convection. Whereas the stiffness matrix due to end convection depends on the problem, wherein which you will be specifying the boundary condition. By this prior knowledge on analysis of heat transfer through extended surfaces, let us move on and solve our first problem on analysis of heat transfer through fins. The problem number 1 states that a metallic fin with thermal conductivity K is equal to 360 watt per meter degree Celsius, 0.1 centimeter thick and 10 centimeter long extends from a wall whose temperature is 235 degrees Celsius. Determine the temperature distribution and amount of heat transferred from the fin to air at 20 degrees Celsius with convective heat transfer coefficient is equal to 9 watt per meter square degree Celsius. Take the width of the fin to be 1 meter. Consider heat convection from right end edge of the fin. Use 3 elements of equal length for modeling. The data given in the problem are thermal conductivity is 360 watt per meter degree Celsius. Thickness is specified. Thickness is 0.1 centimeters. That is, thickness is equal to 0.001 meters. Overall length is given. Overall length is 10 centimeter. Since he is asking us to model the problem with 3 elements of equal length, the elemental length will become 0.1 by 3 meters. Temperature at left end is given, that is T1 is equal to 235 degrees Celsius and the ambient temperature T infinity is 20 degrees Celsius and the convective heat transfer coefficient H is 9 watt per meter square degree Celsius. Also width of the fin is given, which is 1 meter. So therefore the cross sectional area of the fin, which is equal to width into thickness, which will be found to be 0.001 meter square, whereas the perimeter P is 2 times width plus thickness. If I substitute width as 1 meter and thickness as 0.001 meter, I will get the perimeter as 2.002 meters and the surface area is given by the formula perimeter into length of the element. So these are the data given and these are the repeating values which are required to calculate the element stiffness matrix and also the load vectors. Moving on to our step 1, that is finite element model. He himself is given in the question that use 3 elements of equal length for modeling. So therefore I will get 4 nodes and 3 elements. The length of the element is 0.1 by 3, 0.1 by 3 and 0.1 by 3. The boundary condition is T1 is equal to 235 degrees Celsius. We should calculate T2, T3 and T4. We have convective heat transfer for all the elements and also we have end convection for element 3. So this is element number 1, this is element number 2 and this is element number 3. Moving on to our step 2, that is element stiffness matrix. For element 1 we have conduction plus surface convection, that is element stiffness matrix of conduction plus element stiffness matrix of surface convection. If I substitute the formula of conduction formula is given by area of the element into thermal conductivity of the element divided by length of the element, 1 minus 1 minus 1 1 plus element stiffness matrix due to surface convection is given by H A LE by 6 2 1 1 2. Substituting the values, the element stiffness matrix for element 1 will be equal to the cross section area of the element is 0.001 meter square into thermal conductivity is 360 divided by length of the element is 0.1 by 3 times 1 minus 1 minus 1 1 plus convective transfer coefficient is 9. This is perimeter into length. The perimeter is calculated as 2.002 into length is 0.1 by 3 into 6 2112. If I simplify, the element stiffness matrix for element 1 is found to be K of element 1 is equal to 10.8 minus 10.8 minus 10.8 plus 10.8 plus 0.002, 0.1001, 0.1001 and 0.2002. So adding these two, I'll get the element stiffness matrix of element 1 as 11.0002 minus 10.6999 minus 10.6999 and 11.002. Coming for element stiffness matrix of element 2, for element 2 also we have conduction plus surface convection, that is stiffness matrix due to conduction plus stiffness matrix due to surface convection. If you observe, all the values remain same for element 2 also, so therefore the element stiffness matrix for element 2 also equal to 11.0002 minus 10.6999. This completes the element stiffness matrix of element 1 and element 2. Moving for element 3, for element 3 heat transfer is because of conduction plus surface convection and also because of right end convection. Substituting the values, the element stiffness matrix of element 3 will become, for conduction we have area of the element, thermal conductivity of the element divided by length of the element, 1 minus 1 minus 1 1 plus surface convection is given by h times perimeter of the element into length of the element by 6 2 1 1 2 plus stiffness matrix due to right hand convection is given by h times the area of the element 0 0 0 1. Substituting the values, area of element 3 is also 0.001, thermal conductivity is 360 divided by length is 0.1 by 3 times 1 minus 1 minus 1 1 plus heat transfer coefficient is 9, perimeter is 2.002, length is 0.1 by 3 into 6 2 1 1 2 plus convective transfer coefficient is 9, cross sectional area is 0.001 times 0 0 0 1. Now simplifying this, the element stiffness matrix of element 3 is equal to 11.0002 minus 10.6999 minus 10.6999 and 11.0092. This completes our step number 2, that is element stiffness matrix. Element stiffness matrix of element 1, element 2 and element 3. Next, moving on to our step 3, that is global stiffness matrix. The procedure to obtain the global stiffness matrix is already known to us. So using the procedure, the global stiffness matrix is equal to, for element 1 we have 11.002 minus 10.6999 minus 10.6999 and 11.002. So now coming for element 2, adding K11 of element 2 to K22 of element 1, I'll get 11.002 minus 10.6999 minus 10.6999 11.002. Now adding K11 of element 3 to K22 of element 2, I'll get plus 11.0002 minus 10.6999 minus 10.6999 11.0092. So now fill the unfilled positions with zeros. If I simplify these two values, moving on to step 4, that is element load vector. For element 1 we have surface convection. So therefore for element 1 we have load vector due to surface convection, which is given by H P LE T infinity by 2 1 1. If I substitute the values and solve, I will get for element 1 we have H as 9, perimeter is known to us 2.002 into length is 0.1 by 3 into T infinity is 20 degrees Celsius 1 1. If I simplify, I will get the answer as 6.006 6.006. The node number for element 1 are node number 1 and node number 2. For element 2 also we have load vector due to surface convection, and the values are remains same for element 2 also. So therefore load vector for element 2 is also equal to 6.006 and 6.006, whereas the node number for element 2 are node number 2 and node number 3. Moving on for element 3. For element 3 we have load vector due to surface convection plus load vector due to right end convection. If I substitute the values for the formula we have and solving, I'll get the load vector of element 3 as 6.006 and 6.186. The nodes for element 3 are node number 3 and node number 4. This completes the element load vector. Moving for step 5, global load vector. At node number 1 we have only one load by element number 1, that is 6.006. At node number 2 we have two loads, 6.006 from element 1 and also 6.006 from element 2. So adding these two, I'll get at node 2 12.012. At node 3 we have 6.006 from element 2 and 6.006 from element 3. So therefore adding at node 3 we'll get the same value, that is 12.012. At node 4 we have only one load, that is 6.186. So this is at node 1, node 2, node 3 and node 4. The unit is watts. So this completes the step 5 global load vector. Moving on to our step 6, equilibrium equation and application of boundary condition. We know that the equilibrium equation is K matrix into Q matrix is equal to F matrix. We have global stiffness matrix into Q matrix is nodal variables. They are T1, T2, T3 and T4 is equal to F, that is global load vector, which is given by step number 5. This completes the equilibrium equation. Now applying the boundary condition by using elimination method of handling the boundary condition. The boundary condition for the problem is T1 is equal to 235 degrees Celsius. Eliminate row and column corresponding to T1, that is eliminating first column and first row. Since T1 is not equal to 0, multiply the column which we should get rid of in matrix A with the corresponding values of matrix B and take it to right hand side. If I do that, the remaining matrix which I'll get is 20.0004 minus 10. Now minus 10.6999 will multiply with T1, so take it to right hand side. I'll get plus 10.6999 into the value of T1 is known to us, which is 235. 0 will be multiplied with T1, take it to right hand side, it will become minus 0 into T1. 0 will be multiplied with T1, take it to right hand side, minus 0 into T1. So this completes the application of elimination method of handling the boundary condition. Now if I solve this matrix with equations with 3 unknowns, I will get the values of T2, T3, T4 as T2 is equal to 209.625 degrees Celsius, T3 is equal to 194.895 degrees Celsius, and T4 is equal to 189.981 degrees Celsius. So since the nodal temperature matrix is a column matrix, we should take the transpose of this. T1 is given 235 degrees Celsius, T2 is found to be 209.625 degrees Celsius, T3 is found to be 194.895 degrees Celsius, and T4 is found to be 189.981 degrees Celsius. So this completes the nodal temperatures or the temperature distribution along the length of the fin. Now is also asking us to calculate the rate of heat transfer from fin to air. So the total heat loss from fin to air is calculated by heat loss from element 1, heat loss from element 2, heat loss from element 3, and heat loss from element 3 due to right end convection. The formulas is given by Newton's law of cooling, that is HA delta T, where A is the surface area. The temperature difference is given by surface temperature minus ambient temperature. The surface temperature is taken as the average of the element temperature for all the 3 elements. Finally, we have right end convection, which is given by H times cross sectional area into temperature difference. Taking H times the surface area is given by perimeter times length as common, and writing the temperature difference for these 3 elements, element 1, element 2 and element 3, and adding the heat loss due to right end convection, the final answer obtained is 336.05 watts. As asked in the question, we have calculated the temperature distribution, that is nodal temperatures, and also the rate of heat loss from the fin, that is 336.05 watts. This completes the given problem. That's all from this lecture. Thank you.